Why, hello there again. This video is about an AP Calculus related rates circuit. Now, a circuit is a worksheet where all the answers are given to you in a different problem. So we have to solve number one, and the answer to number one will be somewhere in the other problems. Okay, so I'm not going to do it problem by problem, well, answer by answer. We're just going to answer these one at a time. So try and do my best to explain what's going on and how we can set up and solve these related rates problems. Okay, but not actually do any of the solving, just the explaining, because that's really what you need, right? You want it to be explained. You can probably plug in your x values and your y values and your z values and whatever else you have, dx's, dt's, and a variety of different things. So let's just talk about how, right? How we're going to do this. So here we have a rectangle with a constant base. So let's draw this picture of a rectangle, my nicest rectangle ever, 90-degree angle with a constant base of 0.5. While the height is changing at a rate of 1.5 centimeters per minute. Okay, so this is changing, so this is going to get a variable because it's changing. So everything that changes becomes a variable. So we'll call this h, right? Because the height is changing. That's our dh dt, the rate at which height changes with respect to time. Okay, so the question says, at what rate is the area changing when the height is 1.5 centimeters? So we want dA dt, the change in the area, when h equals 1.5, right? Different than the rate of height changing, but still a valid piece of information. So area for the base of our triangle is 0.5 times the height, right? The base is always the same, so that's a constant 0.5. So now we have to differentiate both sides with respect to time. So I get dA dt, right, the derivative of the area, equals 0.5 times dH dt. So it looks like the height isn't even important. So now I can plug in my 1.5 into my dH dt, and that will allow me to figure out how the area is changing. Okay, so pretty okay, yes? So far, so good? All right, a spherical balloon is losing air. That means we have a negative rate, right? The volume is the air, so the volume is leaving at 2,500 cubic centimeters per second. Okay, so that's a negative rate because we're losing air. What is the radius when it's changing at the rate of 25? So we know dr dt, the radius is changing at 25. So we're going to think it's getting smaller, right? If the volume is getting smaller, chances are the radius is getting smaller. So we're going to start with the volume formula for a sphere, 4/3 pi r to the third power. Okay, that's from geometry. Now we're going to take the derivative with respect to time. So dv dt equals, the coefficient comes out, so 4 times 3 is 12, 12 divided by 3 is 4, pi r squared times the derivative of the rate with respect to time. Okay, so let's see, what do we know in our problem? We know dv dt, we know dr dt, so we can solve this problem for r by substituting, dividing, and then it looks like square rooting. So what is the radius? It wants us to solve this equation for r. So plug everything in, do your fantastic algebra, and you'll get the answer. Okay, what else do we have here? Our rectangle's base is once again 0.5 while the height changes. Okay, so what rate is the perimeter changing? This is a perimeter question. So the perimeter has 4 sides, right? We have the height and the height, which are changing, right? So these are your variables. Our other 2 sides are 0.5, which don't change. So the perimeter of our rectangle is 2 heights plus basically 1, right? 0.5 times 0.5, which is 1. So that is never going to change. We're just getting the rectangle is getting taller. So at what rate is the perimeter changing when the height is 1.5? Okay, so once again, this is our rate of change of our height, dH dt, and the height is 1.5. So let's take the derivative with respect to time. So derivative of the perimeter with respect to time is equal to 2 times the derivative of the height with respect to time, plus 0, right? The derivative of our constant 1 is 0, so we don't actually add anything in there. So the perimeter is changing at this rate. So we simply have to plug in 1.5 in for dH dt, and then we can solve our equation pretty quickly. Okay, let's see about this one. A conical paper drinking cup. So that's the shape in a cup in the shape of a cone. Okay, so here's my cone, right? It's vertex down because we want the water to be inside of the cone, not outside. Okay, it has a certain radius. The radius, let's see, the radius of 2 inches and a height of 6. Remember, these are maximums, right? If the water is right here, then the radius is not 2 just yet. Okay, remember, the radius and the height are always going to be proportional when it comes to one of these type of problems, r over h. Okay, how fast is the water level of the cup rising? So that's the dH, the derivative with respect to time of the height. How fast is the height changing when water is being poured in at a rate of 1 cubic inch per second? So that's the volume is increasing at a rate of 1 cubic inch per second. Okay, so let's look at our formula for the volume of a cone. 1/3 pi r squared times h. Okay, notice there's two variables here. There's a radius and a height, but we only want to know the height. So we have to figure out a way to replace our radius with another variable, h. So this is where we come to our triangles, right? We have a proportional relationship between the radius and the height. The radius compared to the height will always be 2 to 6 because that's our maximum radius compared to our maximum height. So we want to solve this equation for r because you want to replace over here. So multiply both sides by h. Radius equals 1/3 of the height when we simplify, right? So over here we're going to come back in and replace r with 1/3 of h. Okay, so I still have my 1/3 and my pi. I'm going to square that radius and I'm going to multiply it by h. Okay, so squaring, I have to square all three pieces. I square the 1, I square the denominator, I square the h. That gives me like 1h squared over 9. And now I can simplify this whole entire thing to one nice equation. That's pi h cubed, all divided by 27. Okay, right, I have a 3 on the bottom, I have a 9 on the bottom, that's 27. Then everything else is a numerator. So now I take the derivative with respect to time of all of my variables. So dv dt equals pi over 27, right? That's a constant, times 3h squared, that's the derivative of h cubed, times dh dt. Okay, so I can plug in all of the information that I know. I know dv dt. I know the height, right? The height is 2. We're told in the problem the height is 2. So I can solve this equation for dh dt simply by doing some algebra to isolate that variable. Okay, so this is an important problem because you want to replace r with h, so we have one equation, or rather one variable in our equation. Okay, profit is revenue minus cost. So here we have a cost function, and here we have a revenue function. Construct the profit function and determine the x value when the rate of change of your profit is this and the rate of change is that. Okay, so let's go back and see what we can do here. Profit is equal to revenue, which is 50x, right? 50x is the revenue, minus our cost function, which is x cubed minus 4x squared plus 50 over x. Okay, so that is our function. Right? I would just take away the variables, or rather the parentheses. P of x equals 50x minus x cubed plus 4x squared minus 50 over x. Okay, so now that the parentheses are gone, we've distributed that negative. Now let's take the derivative. Okay, let's take the derivative of both sides. So you have the derivative of the profit with respect to time equals 50 times dx dt, because every variable gets a rate, minus 3x squared dx dt plus 4x, rather not 4x, that's going to be 8x, right? Because it's 4 times 2, 8x dx dt. Now, what about this guy? Okay, so 50 over x, that's 50 times x to the minus first, right? If we bring that denominator up there. So 50x to the minus first becomes minus 50, so it's going to be a plus, right, because it's a minus and a minus, x to the minus 2. So this is plus 50 over x squared. Okay, so now would be a good time to plug in everything that we know. We know the PDT, right? We know dx dt. So we can replace all these things with numbers. Okay, and that's going to give us kind of a, I don't know, a decimal equation, right? A decimal equation. You're definitely going to want to get a calculator for this one. So you're probably going to want to get a calculator for all these. Sorry, I should have said that at the beginning. Get a calculator. So now that we have a bunch of numbers, the algebra here is about to get crazy. We're going to multiply everything by x squared. Okay, and we're doing this so that we can get rid of x squared here. Okay, so bear with me. We're going to multiply this by x squared. We're going to multiply this by x squared, this by x squared. So we're going to get a bunch of, right, we're going to get a pretty high order polynomial like x to the fourth, okay, with a bunch of fractions in it. But you can do this, right? Just do it one step at a time and do it carefully with your calculator. And then if you have an TI Nspire, once you get your thing down as much as you can, just use NSolve. Okay, NSolve is the best way in a TI Nspire to solve an equation. Okay, if you know how to do that. If not, there are lots of videos on TI's website about using NSolve. Okay, or you can use the graphing part and graph the equation and see when it equals, well, see when it's equal, or see when it equals 0. Okay, and you can solve the equation like that. Okay, so this has definitely got a lot of decimals. This is probably the most intense one on the whole entire project today. Okay, but it's still okay. You can still do it, don't worry. I believe in you. All right, salt is being poured into the shape of a cone. So the cone looks like this, maybe. So that the radius of the cone is twice the height. So the radius is 2 times the height. Okay, so if this is h, right, if we have a height, then the radius is 2 h's. Let's just go with that. Okay, the radius is twice the height. Find the rate at which the pile is growing, right? That's dv dt, the volume. The volume of our pile is growing when the radius is changing at 1/2 of a foot per hour. So we know dr dt is 0.5, and we know the radius is 2.5 at that time. So we have all this radius information, so we want to have a volume formula with just radius in it. So pi r squared times h. Okay, so we're going to come up here and look at our HR relationship. We know that the radius is 2 times the height, which means the height must be half of the radius. Yes, so instead of my h here, I'm going to put an r divided by 2. Okay, so when I simplify my equation, let me simplify my equation real quick. Okay, I have volume equals 1 over, well, let's don't do 1 over yet. Let's see, what's in the top? We have a pi r squared times r is pi r cubed, and I have a 3 and a 2 as denominators, so over 6. So this is my volume formula in terms of my radius. So now let's take the derivative with respect to time. So dvt equals pi over 6 is your constant, right? That's a constant fraction, times 3r squared dr dt. Okay, so we take the derivative of r cubed. Now let's see, what do we know in our problem? We know the radius, right? The radius is 2.5. We know dr dt, the rate at which the radius is changing. So now it's just a matter of plugging everything in and getting the answer. Okay, let's see what we got here. A circle is expanding. So if a circle is expanding, that's talking about the rate of change of the area, right? We have a squared centimeters, so the rate is changing is the derivative of the area. So we know dA dt is equal to 32.5. How fast is the radius changing when the circumference is 10 pi? How fast is the radius changing? So dr dt when the circumference is 10 pi. Okay, let's see what we know. We know that the area is pi r squared. That's the area formula for a circle. So if we take the derivative with respect to time, dA dt equals pi times 2r dr dt. Okay, let's see. What do we know? We know that we know dA dt, right? That's the derivative of the area. We want to find dr dt, so we have to somehow figure out what our radius is. Okay, and to do that, we come to our circumference, right? We're told that the circumference is 10 pi. The circumference formula is 2 pi r. So we can quickly figure out when we divide what the radius happens to be. Okay, so then you plug your radius in here, you divide everything, and you figure out what dr dt is. Okay, so that's how you use the circumference in this point. A circumference helps you find the radius for your problem. Charlie Brown's flying a kite. Okay, so this is going to be a right triangle problem. Okay, so we're saying Charlie Brown is here on the ground, right? The kite was originally 100 feet directly above his head. I know that's not very, correct, but the wind blows the kite in this direction. So we're having this. So dx dt, that is changing the horizontal distance of the kite. Okay, at a rate of 2 feet per second, it says, horizontally. How fast must he release the string? Okay, that's this one, right? We're going to figure out what this rate is. So let's, in Pythagoras, we'll call this a c. So we want to find dc dt when c equals 300. Okay, that's what we're asked to find. So this is a Pythagorean theorem problem. X squared plus 100 squared equals c squared. Okay, so let's take the derivative with respect to time. So this is 2x dx dt plus 0, right? 100 squared is a constant, so it does not have a rate of change, equals 2c dc dt's. So let's see what we know. We know dx dt, right? That's the derivative with respect to time of the horizontal change, so that's 2. We know that c is 300, right? C is 300. We're trying to find dc dt, so it would be really nice if we could figure out what x is. And to figure out what x is, we're going to come over here and make a Pythagorean theorem. So we know that 100 squared plus x squared equals 300 squared, right? C is 300 at this time. So you can figure out what x is, right? The distance here. Find that value using Pythagoras, substitute it into here, and then we can easily figure out what dc dt, the rate that the hypotenuse, I guess, is changing. Okay, so we got to do some extra stuff here. Okay, a 13-foot ladder slides down an exterior wall. So here's our ladder problem. 13 foot is the constant, right? It's sliding down, so that's going this direction, your y direction. So dy dt is 1 foot per second. How fast is the base changing? Right, we want dx dt. How fast is the base changing when x equals 5? Okay, so let's do this. This is once again a Pythagorean theorem problem. So we have x squared plus y squared equals 13 squared. So 2x dx dt plus 2y dy dt equals 0, the derivative of our constant 169. So let's see what we know. We know dy dt, right? That's sliding down at a rate of 1. We know x is 5, right? X equals 5. We want to find dx dt, so that's our variable. So we need to figure out what our y value is. So once again, let's come over here and do a little Pythagorean theorem. We know that y squared plus 5 squared equals 13 squared, right? When x equals 5, we can figure out what our y value is. Okay, so once you figure out what your y value is, we plug that in here. Okay, and now we have a bunch of numbers, and you can solve this for dy dt. Okay, so hopefully you're getting the idea of how to do these problems, right? We start with a formula, you take the derivative, and you figure out what we need to do. Okay, sometimes you have to solve for more than one thing using multiple equations. If you're smart enough, you can do it. The volume of a cube is 125, okay? So we have a cube, three-dimensional figure with all the same sides, right? A cube has 3 equal sides. So volume of a cube is x cubed and is changing at a rate of 8 centimeters. So this is our dv dt. How fast is the surface area changing? Oh, it's a surface area question, okay. So if you look at the surface areas, that's the sum of all the surfaces. There are 6 squares in a cube, so the surface area is going to be 6 times x squared, which is the area of one of these sides, right? X times x is the area of one of those sides. So how fast is that changing at when the volume is 125? Okay, so let's take the derivative with respect to time. The derivative of the surface area with respect to time is equal to 12x dx dt. Okay, so we know how fast it's changing, right? We know that the volume is changing. How can we do this? Let's see. We know that the volume is changing. So that's over here on this question, huh? dv dt. We need to find out what dx dt is. So dv dt equals 3x squared dx dt. Okay, so we need to figure out and solve for the rate at which x is changing. Okay, so we know dv dt, right, that's 8. What is x? What is the side of our cube? Well, if our volume is 125 equals x cubed, I think we can pretty easily say that the x value is going to be 5. Okay, so we can use this setup to figure out what our dx dt is. Okay, so we know our x value is 5 still, right? We have the same x value, and we just calculated dx dt, so now we can find what the surface area rate of change is once we do that. Okay, ooh, that was a 2-part problem. That one's pretty tricky. Okay, take the volume, find dx dt, and plug that into the surface area, dx dt. Oh, nice problem. Okay, I think this one's pretty simple. Maybe you do too, but maybe you're not. So let's try and see. A right triangle has legs x, y, and z. Okay, x, y, and z. X, y, z. At what rate is x changing when we have all this other information? Okay, so we have x squared plus y squared equals z squared. So 2x dx dt plus 2y dy dt equals 2z dz dt. So we know what y is, check. We know what dy dt is, check. We know what z is, check. We know what dz dt is, check. So in order to solve for our variable, which is dx dt, I need to first calculate my x value. And I'm going to do that with, once again, Pythagoras. So 4 squared plus x squared equals 5 squared. That allows you to figure out x, and then you can solve this equation for dx dt. Okay, our last one, 2 snails start moving away from each other in a garden. One goes north at a rate of 10 centimeters per hour, and one goes east at a rate of 3 centimeters per hour. After 2 hours, so after 2 hours, this snail has gone 20 centimeters and this snail has gone 6. So what is the rate of change of their hypotenuse? Okay, the distance between them. Maybe we'll call that d for distance. How about that? Or x is fine. So once again, this is a Pythagorean theorem problem. X squared plus y equals, let's see, plus y squared equals z squared. So 2x dx dt plus 2y dy dt equals 2z dz dt. Okay, so we know your x value is 6, right, after 2. We know dx dt is 3. We know your y value is 20. And we know dy dt is 10. So we can once again use a little Pythagorean theorem. 6 squared plus 20 squared equals d squared. Why did I put z? I don't even know. Z was the last one. I meant d, right? The distance, the hypotenuse. I guess it doesn't really matter, does it? Whatever you called it, keep calling it the same thing. So we can figure out what d is, and then you can solve for the rate at which that is changing. Okay, so there you go. There is an explanation about your related rate circuit. Make sure you have a calculator because a lot of these are going to be decimals, as you can see from the answers. Okay, I hope you're having a great time, and I will see you later.